It just felt weird.
Two problems here that I think will be very helpful to you. So let's look at, this is a little different than, in fact, is this like the one I gave you guys in class?
Yeah.
Okay. So let's go through one of these together. Difference being from what we've done before, that this one is being launched, in this case the stone is being launched at an angle, it's not being launched horizontally, right? Okay, so that makes things a little bit trickier potentially. Same idea. So what we want to do, we want to figure out how far does the stone land from the base of the cliff, and
Is this the
what?
one we were just trying to figure out?
Yeah.
Right?
Yeah. So if you guys have worked on this, let's talk about how to finish it.
Yeah.
Okay. So we can draw. Do you want to draw a picture?
Yeah.
No.
It's not much of a picture, really. That's our picture. Here's the velocity vector, so it's going to be we'll just call that theta. Theta is 11.2 degrees. Initial speed is 40.7 meters per second, right? And so we need to figure out then, we need to know, in order to know how far the stone lands from the base of the cliff, what are we probably going to have to figure out? Time, yeah. Because we know that we're going to break the stone's motion into horizontal and vertical components, right? And the horizontal stuff is pretty simple, but when well, let's just do that. So we've got the x components and the y components. What do we know? Well, we can take our original vector and we can actually figure out what the horizontal and vertical components are, right? We know that the initial velocity is 40.7. So if I take my initial velocity vector, 40.7 at an angle of 11.2 degrees, what is V naught sub x going to be?
It's the opposite over adjacent, so R10.
Okay, so this is the 40.7. This is the right angle, right? So we're trying to find this guy. This could be a cosine issue, isn't it? Right? So we know it's a component. So we know we're gonna multiply our vector.
Is that initial vector, is that to go with the triangle or is it the bottom of the cliff?
Oh no, it's just this triangle right here is all it is. Yeah. And so the cliff, if we want to add the height of the cliff, 63.3 meters. Okay. And that's supposed to be a 40. That's a 0. Can't read my own writing. Okay.
Why is the vector opposite to the 11.2 degrees? Why isn't that vector going down?
Say it again.
Why does that vector go up instead of down?
Because the initial velocity is inclined up at an angle of 11.
Yeah, like the 40.7, I understand why that's like going up, but like the one next to it, that's just going straight up and down.
Yeah.
Why is that vector going up?
Okay, because remember what we're trying to do is we're trying to take the initial velocity vector and break it up into horizontal and vertical components that we could add tip to tail to give us that, right? So to get from the tail of that vector to the tip, what am I going to do?
Yep.
Going to go this direction horizontally and that much vertically. Okay? And that makes sense, doesn't it? Because initially, if we were looking at this, and this is kind of a good little mental test to do on problems like this. If I were looking at this thing straight on, I would be isolating the vertical component of the rock's motion, right? Initially, it would look like somebody just tossed it up in the air from this perspective, and then it just went down all the way to the ground, right? From looking from above, I would just isolate the horizontal component. And we know the horizontal component of velocity during projectile motion is what? No. Is what? Constant. Yeah, the horizontal component of an object's velocity that's in free fall, projectile motion probably, is constant, because there's no acceleration acting on it. The acceleration is vertical, not horizontal, right?
So when we look down, it looks like a straight line.
Yeah, we look down, it looked like something just traveling along at constant speed.
Got
Yeah. Okay, so the x component of initial velocity then is gonna be my initial velocity, so the overall vector times either sine or cosine every time, right, to make it smaller. In this case, it's gonna be times cosine because it represents the adjacent side of that right triangle, right? So we can add that up here. So we know that V naught, and it stays the same, right? So really just V sub x is always 40 cosine of 11.2 degrees. And that's constant the whole time. What else would we know? I guess, what's our initial horizontal position? So x naught is what? Zero, yeah. Okay, eventually we're trying to find x, our final position,
So it's supposed to be 40.7, right?
40.7, yeah.
Are we breaking this into two?
Oh, right here it is, you're right, sorry. Yeah, let me fix that.
And it's okay.
No, that's good, I should fix that. Okay, so there's everything I have for x, not very much. Not enough really to do anything with, right? What do I know for y?
The initial. You said actually that.
Yeah, v naught sub y is gonna be,
63.
okay, well, okay, and in terms of,
40.
Sine.
so 40.7 times the sine, good, times the sine. So we'll just write that over here. So we know that the initial, oh man, am I not, oh I am, good. So v naught sub y is our initial speed times the sine 11.2 degrees. Okay, what is our initial position? So y naught is
63 meters.
63.3. What's our final value of y? 0. Okay. We're trying to find some stuff. Eventually we're going to want to know, if we want to know how fast the stone hits the ground, with what speed the stone hits the ground, we're going to need to know the final y component when it hits the ground of its velocity. Okay, but I can't find that without a little bit more information. What else could I calculate here? Actually, I probably could, but what do I need for over here? What's my acceleration too? Yeah, good. I know the acceleration in the y direction is just negative 9.8. Good. Okay, that helps a lot. Now I can fill in a lot of stuff over here. What am I missing in the x column?
Acceleration?
Okay, that's 0, right?
Oh.
Right. But I'm missing something. There's something there I need.
Oh, sorry, I was just gonna say, I think your V naught sub y is wrong. It should be 40.7 tan.
No, there shouldn't be any tangents in there. For this one?
Yeah.
Okay, because look, here's the,
Yeah.
there's the angle, there's theta.
Mhm.
There's the hypotenuse, and that's the opposite, right? So it's gonna be sine,
Oh.
right? And the thing is, you always know, you don't even really have to give that one a whole bunch of thought, because every time, it's never gonna be any different. Whenever you break a vector up into components, it's always gonna be the overall magnitude times sine or cosine, every time.
Is it x is going to be the cosine and y is going to be the sine?
Right, so y is the sine. So this is 40.7 sine, I'm just gonna call it theta. Yes, sir?
Wait,
Oh. Go ahead. 40.7. Go ahead. It's really.
But it's not always, x isn't always cosine though. X
No,
is
it wouldn't
sine.
have to be. No, it depends on the angle you're talking about, sure.
How did you know that the hypotenuse is the initial velocity?
Because the initial velocity is inclined at an angle, right?
Okay.
If the initial velocity were not inclined at an angle, then this problem becomes pretty easy, like the last one we did, where the initial velocity was horizontal. Then we would just know that the initial horizontal, or the x component of velocity would have just been like 40.7 if it were just traveling horizontally. The initial y component of velocity would have been 0, right? See what I'm getting at? If it's at an angle, then you guaranteed what you're trying to do every time is you're trying to break this vector that's at some weird angle up into convenient right angle components. So it's always going to be the hypotenuse.
I thought you knew, why'd you put 40.7 sine theta when you know it's?
I do. I know. I just didn't have enough room to write theta.
Oh,
Theta is
sorry.
just 11.2. Yeah. Okay. So what we're missing then, would you agree, is time?
Yes.
If I knew what t was, it'd be really easy for me to find how far this thing traveled, right? Because I would use the kinematics equation. In this case, it would just be x equals x naught plus v sub xt.
When did we make that?
Well, we didn't. We called it this. We called it d equals d naught plus v bar t.
Oh,
Right.
so we're substituting.
Well, yeah, but isn't that convenient to do for us? Because we know x represents a horizontal position and y represents a vertical position. So rather than call something like d sub x, well, that's really just x, isn't it?
Oh, okay, so that's what we did.
Okay? So we need t though. Well, where can we get t? Well, from this side, right? We can go over here and find out what t is. Did I start? Oh, that's right. Okay. So if we want to find out what t is, then look what we know up here. What kinematics equation could we use to solve for t, given that, and that?
The big guy.
The big daddy, right? Okay. So we know then that we can use the equation. What was that? This thing is freaking out on me. So y equals y naught plus y component of velocity t plus 1/2 a sub y t squared. Right?
That's a lot of letters.
Yeah. Okay, and we're gonna solve for t, right? So what stuff do we know? Well, we know this is 0, right? And then this is stuff we've got to solve for, probably using aqueduct or using polysmoke too. We're gonna get a quadratic equation. If we plug this stuff in, what do we get? Well, we get 0 equals 63.3 plus v naught sub y. Well, that's inconvenient. That's a weird number, but that's okay. I mean, that's just a number, right? Plus 40.7 sine 11.2 degrees t. And then this is going to be plus 1/2 times negative 9.8, so that's minus 4.9 t squared. Right?
Right, so then we just solve for t, right?
So now we've just got to solve for t, exactly. Okay, so
What is t?
okay. And it's possible it would be easier maybe to solve for v sub y first and then not have to use the big daddy.
Wait, solve for v sub y?
We could, because we could use the one without t to solve for v sub y. But we'll do it this way. I mean, there's other ways. There's a bunch of different routes we could take here, depending on which kinematic equation you want to use first. We'll use this one. Being as we have technology, I want to illustrate how you use this anyway. So in our calculators, we'll go down to apps, polysmoke 2. Open this thing up, and we're going to do polynomial root finder. Real, decimal, sounds good. Second order, so next. Okay, so a sub 2, well that's, the coefficient of t squared is negative 4.9. What's the coefficient of t? Well, it's that, right? So we've got to do 40.7 times sine of 11.2. Make sure we're in degrees, right? Which I am. And then my constant is 63.3. Okay, solved.
Mr. O'Leary?
Yep.
Can I do that on the
So it gives me two answers. I get positive 4.49, blah, 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 negative 2.87, blah, blah, blah. Which one do we keep it?
Positive.
The positive one. Yeah, we want the one that occurs after we launch the rock, right? Not before we launch the rock. So we'll take, that's our value for T. And I'm gonna, I wonder, can I save that thing somewhere?
No.
From the, does anybody know if I can? We know how I can grab this number from this program?
It always like goes away after.
It does?
He's not on Aqueduct, though. Are you talking about Aqueduct? Is that what you're
Well, I have problems with that.
I would guess,
Ooh.
oh, store. Oh, can I store that? Let's
If
try
you hit
that.
store, goes coefficient.
Coefficient, store roots to list.
I don't know what that.
Okay, that's what we want. Let's just try this. Let's just mess around with it. So store roots to list. Okay. X list we're gonna store as, I'm just gonna call it alpha A. Okay? Alright. So how do you get it back? I go recall alpha A, which we'll do in a second. So we got that. I'm gonna write it down anyway though, just in case. 4.029
Oh, it's there.
6. It is there? Okay.
That's supposed to be on the other side.
Okay, so
But it takes both of them.
okay, so now if I recall,
You have to go to this.
recall alpha A. Oh no, I have to go to list.
So second stat.
Oh, okay.
And then
There it is, 7. Yeah, good.
But then
Okay.
exact.
Right, so this is gonna be probably harder than it's worth, but so then what I probably have to do.
Wait,
is
no. Go up there. Go up like you were.
Yep.
Okay, press enter. Oh, you don't get them back, no mind. I was thinking you might get those numbers back and you could delete.
Now, I think what I have to do then is I probably have to go up to this list. This is probably gonna be more trouble than it's worth. If I go that list, oh, see, I don't know how to do it on here. It would be like sub 1 would be the,
Oh, well, that's what paper pencil is.
yeah, maybe that's not worth, maybe that's gonna be more trouble than it's worth. I can't read this thing very well either. Not probably worth it.
Yeah, I think it's go on the board. Right. You would be winning. That'd be 400.
You know, this is the second time since I'm talking. I changed his batteries.
Oh, I know what I can do.
I'm like, you know, it's really sad since I don't have something to buy.
Can you scan the fingerprint and onto that?
What are we doing?
Good question.
Do we have a technical issue?
No, it's just, it's not worth messing with. Okay, so I'll look into it later. I'm not gonna waste your time with it now. So anyway, so we got this time, right?
Yeah.
So if we know t, then now we can do a bunch of stuff. Now we know what t is. It's
Is T the same for X?
It's gotta be same rock, right? So wouldn't you agree that the frame in the movie when the rock is hitting the ground is what we found, right? That's the frame that we want, isn't it? That's the frame we want over here, because we want to know when the rock hits the ground, how far did it travel? What's the value of x, right? So 4.490290266. We're not going to keep all those, of course, but when we're making our calculation, I'm going to. So then if I want to find x, that's easy to do. X is just 0 plus my initial and final and constant x component of velocity times t, right?
Wait, I thought X sub 0. Yep. Oh, never mind, I wrote down wrong.
Okay, so then we'll just multiply 4, I'm going to do this, I'm just going to store this number, 4.490290266. There, now I can go grab it whenever I need it. So that number times this number, 40.7 times cosine 11.2 degrees is that.
Isn't the average though?
Okay, sure, it's the average, but the x component of velocity is its own average always because it's constant. See what I'm saying?
So that's the velocity answer then, right?
So that is,
Meters.
that's the position.
Okay.
Okay, so we just calculated position. How far did it travel horizontally? Okay. So rounded to, I think we got what, 3 places?
Yes.
So 179 meters is how far it traveled. Okay, we want to know how fast did it hit what was the speed when it hit the ground, I think. Is that what it was asking?
That was the second part.
Second part, okay. So to find the speed with which it hits the ground, we've got to solve for this guy. Okay, don't get sidetracked. Everybody see this? So we got to be able to fill that in. Well, what's the simple equation we're going to use to solve for v sub y now?
V equals V naught plus AT.
There you go. V equals v naught plus AT, right? So for us, it's going to be, with the y's, it's going to be v sub y equals v naught sub y plus a sub yt. Well, we know that stuff. That's equal to, this one was 40.7 sine 11.2 degrees plus negative 9.8 t, right? So minus 9.8 times t, that big long number, right? We'll check it, that number. Right, so what do we get? So we get 40.7 sine 11.2 minus 9.8 times that guy. Gives us that. So my velocity is negative, right? What's that mean? It's going down. Yeah, the vertical velocity is negative, which of course it is, right? Okay, so negative 36.099, blah, blah, blah. We got it on there, right? Okay, so if I want to know the speed that it's going when it hits the ground, what am I going to do here? Not even just absolute value. Now think about this thing. When the rock is hitting the ground, it's traveling downward. It's got a component of horizontal velocity and a component of vertical velocity, right?
Yes.
So it's going to be hitting the ground. When it hits the ground, probably it's coming in at some angle, right? We don't know what the angle is. But the velocity, the final velocity is going to be its speed times the angle that it hits at, right? How do we know? Well, we could even find the angle because we know that this velocity vector, the final velocity vector v, is just built from v sub x and v sub y, added at right angles. See what I'm saying?
Yes.
So if we want to know the angle this is coming in relative to the horizontal, well, we could maybe solve for this angle more easily, and then just subtract from 90. But I didn't ask that. We could though. Everybody see that? We could solve for this. If I wanted to solve for that angle theta, isn't that angle theta just equal to the arctangent of v sub x over v sub y, both of which I know on my lists, right? And everybody with me?
Do we have to do that?
No, we don't, but we could. All we have to do is plug it in a calculator and we find out what it is. Okay, but what we do want to know is the length of this thing. Well, how do I find the magnitude of the speed? How do I find the magnitude of v? If I know those two parts. Yeah, Pythagorean theorem, right? Right, so we know v squared equals the square root of v sub x squared plus v sub y squared. So let's do that with our numbers up here. So we've got, there's our number for v sub x, right? So we're going to do the square root of, I wish I just had that number up there somewhere. I should, but I don't. Oh yeah, I do. No, I don't. Never mind. 40.7 cosine 11.2. I got to square that whole thing, right? So I'm going to add another set of parentheses. Should have done that to begin with. So I've got that whole thing squared. Right, there's v sub x squared plus v sub y is
Negative.
that one right there, the negative 36, right? In parentheses, because I'm squaring it, squared, and so that's it.
Wait,
But then you have to take the square
doesn't
root
this
of it.
square
I did square root it, right?
So the rock
But
only
v
went
squared
53.8
equals.
So no, so that's how fast it's hitting the ground at a speed of 53.8 meters per second,
okay, okay.
Wait.
right? Because what we did is we just calculated this. I just plugged the numbers in for that. Whoops.
Okay, that's what we're getting hung up on. And then, doesn't the squares just cancel out the square root, so then you just have,
No, because they're being added, right?
oh, and then you have to take the square root?
Yep.
So that's different?
But it's just, I'll do it on a calculator.
True.
So 53.8 is the last piece of that puzzle. Meters per second.
And why wasn't it 36?
Say it again.
Why wasn't it negative 36?
Because negative 36.09 blah blah blah. Hey, that's only the part, the vertical component, right?
But
we
it's
said it-
one driving
Because it hit the ground. We said it hit the ground with that vertical component of velocity, and the horizontal component stayed the same the whole time, right? So we had to combine those two, but they combine as a vector. They combine, right?
Okay.
There's the vertical. If I want to put numbers on it, that was the roughly, well, the magnitude was 36 point something, right? This one, we never knew what the number was. Okay. So, does that make sense? Okay. So should we try it? See if it worked? So so let's see, let's moment of truth here. So what did we get for what was our distance? Anybody write it down?
179.
What was it again?
179.
It was? Oh yeah, there it is. I see it. 179 meters.
Meters, 30 meters.
Oh, thank you. It's already there. And the speed was 53.8. Let's see how we did. Bingo. Okay. We got it.
Is this on the assignment that has just 2 questions?
It's on a short.
It's the one
Yeah.
that we did Friday, but we did.
Yeah.
Yeah. It's on an assignment, but I can't remember. It's on one of them. Yeah. Third one, there it is, all right. Make sense?
And what's that one do?
In 4 minutes.
Oh, darn it. So we're
This
We're out of luck.
good job. When is this that assignment due? The third one?
So say it again.
When's the third assignment due?
Well, you tell me. What should it be
Let's
due?
just keep them open.
Oh, I'll keep them open.
Well, it was like, why did?
I'll let you work on this. Yeah, tomorrow you can work on it. Let's just set all this stuff due at the end of the week.
Okay.
And I'll add something different like halfway through the week, but that'll give you all week to get all your questions answered. Okay, I'll put that on the calendar.
So you're gonna work it?
Some didn't.
No, means you get some work days. I'll give you a couple work days this week, but yeah. Okay, good.